everybody. My name is Eric Williams, and I want to welcome you all to our Parking Structure Durability Educational Webinar Series. It's a new series proudly hosted by the Concrete Preservation Alliance. Over this four-part series, industry experts will guide participants through conversations regarding inspection and assessment of parking structures, post-tension system rehabilitation strategies, as well as targeted corrosion mitigation design and long-term global protection planning to ultimately provide a practical framework for durable parking structure solutions. Today's session is going to be titled From Visuals to Data, Modern Inspection and Assessment for Parking Structures, where our presenter will do a deep dive into tools, case studies, and lessons that help engineers and owners discover what is happening within their parking structures so they may develop an effective preservation plan. If you are new to the Concrete Preservation Alliance, welcome. We are a coalition dedicated to promoting best practices in concrete repair and preservation. Our mission is to offer free, accessible, and non-commercialized education, sharing practical knowledge from professionals in the field to support long-term durability and sustainable infrastructure. We extend our sincere thank you to everyone and to all our members and supporters worldwide whose collaboration and dedication make the Concrete Preservation Alliance and educational events like this possible. And if you ever miss anything, if you'd like to watch any replays of this or past sessions, or you can download the presentation slides, our website, you can do all that on wesavestructures.info. And while you're at wesavestructures.info, you can also check out our environmental impact calculator. This is a free tool that helps you estimate the environmental benefits of repairing versus replacing concrete structures. This tool helps show the vast impact that replacing concrete structures has on the environment and why we focus on saving those structures instead. And before we begin, just a quick note, one of the best part of our webinar series is the audience participation or the audience questions. So please don't hold back. You can post your questions throughout the webinar into the chat. Just make sure to include your first and last name when you post, because at the end, we'll be giving away a $100 Amazon gift card to the person who submits the best question. Our speaker will be able to choose that, and you can, you'll be contacted by email to claim your prize. So speaking of speakers, let's meet today's presenter, and that is Pratik Mercute. He is a professional engineer and a NACE CP specialist. He works as a senior product manager at VCS Engineering based out of Tampa, Florida. Pratik has been with VCS Engineering for 5 years, leading numerous projects throughout North America and specializing in corrosion forensics. Pratik has a background in metallurgy, as well as a PhD from Oregon State. So Pratik, we really appreciate you taking time out of your busy day and able to share a little bit of knowledge here. So I'll throw it over to you, Pratik, and thank you.
Thank you, Eric, for that introduction, and welcome everyone. And thank you for taking time to attend today's presentation. Today's presentation will focus on investigation of concrete parking structures, and primarily I'll be focusing on conventionally reinforced concrete. We also do investigations or pre-stressed and post-tensioning structures, but those topics will be covered in the subsequent presentations. In today's presentation, I'll briefly talk about the energetics of corrosion, why it happens, how it happens, and then go into details about what typical investigation tools we use to assess the condition of our parking structures, and then go into the conclusions. So when we are talking about steel in concrete, we never find steel as is in nature. We always find steel in the form of iron ore. And these iron ores are pretty brittle and they do not possess any engineering properties, so to speak. And that's why we need to process them, add a lot of energy into it so that we can get a very usable product like steel, cast iron, ductile iron, or wrought iron. Now, iron ore is a very low energy mineral that's found in the earth. We add a lot of energy and we make steel out of it. And that's the steel we use as rebar, sheet pile walls, pre-stressing strands, or post-tensioning strands. When these strands are exposed, or when the steel is exposed to environment, it starts corrosion or it rusts. And this is where Mother Nature does what it does best. it will try to take that energy back we put in the first place. So effectively, you can think of corrosion as reversal of energy, where corrosion is just one way to take that energy back and put it back in the nature again. When the steel corrodes, it forms rust on it, and the rust is essentially the iron oxides and hydroxides, and effectively that's the same thing we started with in the first place. So we started with mineral ore, that is a low energy product. We added a lot of energy into it, made it into some engineering products like rebar or uh, post-tensioning strands. And then when it rusts or when it corrodes, it forms iron oxides and hydroxide, which is effectively the same thing we started with. So effectively, think of corrosion as completing the energy cycle. You start from low energy, you go to high energy, and then come back to the low energy. In context of corrosion of steel, corrosion itself is an electrochemical reaction, meaning electro is the electronic part where you're talking about transfer of electrons through a metallic conductor, which can be a rebar. And the chemical portion of the electrochemical reaction is transfer of ions that happens through the electrolyte. In this case, concrete can be an electrolyte. It can also be soil or water. For any corrosion reaction to happen, we require four components. Anode, which is where the section loss happens, which is where the rust forms, which is where that you see brownish reddish rust product. Cathode is the protected part of the structure where the electrons are accepted. Anode is where the electrons are released. Cathode is where the electrons are accepted. Metal is where the electron transfer happens. And electrolyte is where the ionic transfer happens. So for any corrosion reaction to occur, you need four components, ACME or ACME in short. If you try to remove any one of these four components, you can stop the corrosion reactions, but it's easier said than done. It's extremely difficult to remove any of the four components. So we are just trying to mitigate corrosion. And in context of steel and concrete, this is a really good example where you see anode formation and a cathode formation on the same rebar. In the picture on the bottom left, you see an anode on the right side for the lower rebar. That's where the rust is forming. Whereas on the left side, that's your cathode, that's the protected part. M is the rebar itself. It can be a post-tensioning strand or a pre-stressed strand. And the electrolyte is the concrete itself. So ACME is what you need for any corrosion reaction to happen. We know concrete is highly alkaline. pH is typically of 12.5 to 13. But concrete is like a hard sponge. It will absorb anything and everything that comes in contact with it. It can be chlorides from your de-icing salts or from marine exposure. It can be acids from your soil. It can be carbonation or carbon dioxide from your vehicle emissions in your parking garages. So it will absorb anything that comes in contact with it. If these species get to the rebar, that is what causes the corrosion of steel. It does really well in compression and does poorly in tension, and that's why we need reinforcing steel. Speaking of reinforcing steel in concrete, if your steel is embedded in good quality concrete or a highly alkaline concrete or high pH concrete, you form a passive layer or a passive oxide layer on the steel surface. This oxide layer is essentially what protects the steel from further corrosion. The higher the pH or the more alkaline the pH, the better is the quality of the film that forms on the steel. But as I said, concrete is porous in nature. Carbon dioxide gets in, chlorides get in. A lot of species are absorbed and adsorb onto the concrete. And most of these species, they need moisture for propagation or diffusing through the concrete. And when these two species get into the concrete, they get to the rebar. That's where that passive oxide layer I was talking about, that gets destroyed. And that is essentially what we call as corrosion or formation of rust. The process itself is called depassivation because we are destroying the passive layer. It's called depassivation. And carbon dioxide and chlorides are the two key species we often encounter in field. This is not exclusive, like a exhaustive list. There are so many other species that can cause corrosion or depassivation, but the key culprits in concrete parking structures is essentially carbon dioxide and chlorides. Typically, these two species need water for diffusion, as I said. So A good rule of thumb is follow the water and you will probably see an issue with your concrete, or you'll see corrosion issues in your concrete. So follow the water. Now, why is corrosion such a big deal? The problem is when you're dealing with steel, you're dealing with iron in the steel, right? Let's assume the volume or the relative volume of iron is 1. All the corrosion products that form on the steel have a significantly higher volume than that of steel or the iron. And you need space to accommodate that expansive volume of these rust products. Essentially, you do not have any space between the rebar and the concrete. And rust, that expansive rust, would need some space. So what happens is when you have a good quality concrete, the passive layer is there, then your chlorides get in, your carbon dioxide gets in, your acid gets into the rebar, and that causes depassivation. When the depassivation happens, the rust formation starts, and that rust will push the concrete out. And we know that if concrete is subjected to tension, it does not perform well. In tension, you will result in formation of cracks in the concrete, and severe cracking can result in spalling and delamination. Now, as soon as the crack forms, you have a direct pathway for the chlorides and carbon dioxide to get in. So once the crack forms, you have even more severe corrosion rates because of the crack formation. That's a direct pathway. So one needs to be mindful about the cracked concrete because that's where the corrosion rates might be higher. And the corrosion is such a big issue just because of the expansive nature of the corrosion products that form on the iron. Now we know how corrosion happens, what the energetics are for the corrosion. The question is, how do we better understand our structure? How do we assess or evaluate our parking structures? There are many techniques at our disposal. Some of them are non-destructive, where you do not really make an impact on the concrete. Some are semi-destructive, where you would have to drill a hole to make a connection to the rebar or something on that lines. And some of them are destructive, where you need to take a sample from your structure and analyze it for a few properties. And I'll talk about these in the subsequent slides. Visual inspection is one of the most primitive techniques we use, where we rely on visual signs of degradation or deterioration. We often run into a fluorescence issue where you have excess moisture going through the concrete. You see spalls, you see rust staining, you see water staining, you see a lot of rust staining here on the double T beams. In some cases where you have, let's say, metal pan deck supporting the concrete slab, you can see severe section losses in that. But by the time you see these issues, it's often too late in the degradation cycle. And the corrosion has already advanced to, has progressed to really advanced stages. But we need to act preemptively. You cannot really wait for these signs to show up and then act on it, because by then the cost of repair or mitigation would be too high. So it's best to preemptively act on these. And that's why you cannot solely rely on visual inspection. The other technique we often use is hammer sounding or chain drag, where you take the hammer, you sound the concrete, and you hatch out the area which sound delaminated. And the question is, does the damage stop there? Well, not really, because hammer sounding can only pick those areas which are audible to human ears. It cannot pick up the areas that extend beyond those delaminated areas where micro cracking might be present. Hammer sounding cannot pick that up. The question is, does the damage stop there? Well, not really, because beyond that area, beyond the micro cracked area, you have areas where active corrosion is still happening, but has not progressed to the extent that it will cause micro cracking or cracking or delamination of the concrete. So when you are solely relying on hammer sounding and visual inspections, you need to be mindful that there are limitations to these techniques, and these can severely limit your detection of the defects in your concrete. So in addition to visual inspections and delamination surveys, you often use different techniques. One of them is ground penetrating radar. GPR is a very simple electromagnetic tool where you send electromagnetic waves into the concrete and you analyze the reflections coming back from any of the steel present or any of the interfaces that are present in the concrete. This is a schematic of how typical GPR data looks like. Every peak you see on this image is the presence of a rebar or a metal object. That can be a rebar or a post-tensioning strand or a pre-stressed strand. GPR is really good at locating metal object or objects with different dielectric properties within your concrete. People often use it for concrete cover depth analysis, which is essentially measuring the distance from the surface to the top of the peak here. The concrete cover depth information is very critical for service life because the higher the concrete cover, the more service life you can expect out of your structure. Because it's going to take a longer time. If you have a higher concrete cover, it will take a longer time for chlorides or carbonation to get to your rebar and start corrosion process. On a lot of projects, we often do concrete cover depth surveys and we plot heat maps to represent how the cover depth looks like. This is a cover depth survey we did on a parking garage that was connected to a hospital. And the top level shows we have really good cover towards the center, but going towards the edge, you see relatively lower concrete covers. So you can visualize concrete cover depth information in terms of the heat map. That will give you a spatial distribution of the areas with low concrete cover and also areas with high concrete cover. And then when you can take a very informed decision as to, okay, these are the areas you need to focus more attention on because the chlorides have might already gotten into the concrete, to the rebar, and in some areas you have adequate cover depth. In addition to concrete cover, we also use GPR for determining the layout of the rebar or the reinforcing steel that's present in the concrete. In most cases, you do not have as-built drawings, and GPR can be used to locate or to determine what's the layout. Just by measuring the distance between these two peaks, I can tell, okay, this is my rebar spacing, or this is the spacing between my post-tensioning strands, and GPR can give you that information. It can also tell you how many layers of rebar or how many mats of rebar that are present in the concrete. Obviously, that comes with a caveat, but you can determine how many layers of rebar are present. The image on the bottom right shows spacing for a welded wire mesh in the concrete deck that was supported by a metal pan deck. So GPR is really useful when you're trying to have some load rating efforts done or to determine the rebar layout in the absence of as-built drawings. In some cases, we use GPR for amplitude analysis. Essentially, we are looking at the strength of the signal that's coming back from the concrete. You see on the right side, you have very sharp peaks, very clearly defined peaks. Whereas on the left side, you have attenuated signal, or you don't have any sharp peaks, or you have diffused peak. This is an indication that concrete has potential defects. Amplitude analysis cannot tell you what kind of defect that's present in your concrete. It will only tell you this is the area where a potential defect exists, and you need to investigate further. Some companies or some people claim that it can exactly tell you what kind of defect, but you can have the exact same signature, GPR signature from two different defects. And that's why you cannot solely rely on GPR to tell what exactly is the nature of the defect. This is the same parking garage we did the amplitude analysis on. And this is kind of interesting because towards the center, we saw significantly higher concrete cover. But at the same time, the attenuation or amplitude analysis shows us a different perspective on the data. We see a lot of defects have formed towards the center where you have adequate cover depth. So you might have adequate cover depth, but if it's micro cracked or if it's a pore strip or if it's a different material, you might have defects into the concrete or you might have inferior quality of concrete that can be easily judged by GPR. Again, GPR should not be used to determine what kind of defect it's present. It can only be used to tell, okay, this is the potential area where the defect is present. You need to investigate further. So this is a really good guiding tool. In addition to GPR, we often do concrete resistivity surveys. It's a quick and easy test you can do in the field. Effectively, concrete resistivity is a measure of resistance to the flow of corrosion current. The higher the resistivity of concrete, the lesser the risk of corrosion. This is kind of a table showing a ballpark range of where the resistivity values would land and the associated risk of corrosion. As I said, if you have a lower resistivity or a highly conductive concrete, you have high risk of corrosion. Whereas if you have highly resistive concrete, you have low risk of corrosion. That being said, resistivity surveys are very prone to environmental factors. If your concrete is extremely wet or very dry, your resistive values are going to change. If your temperature at which you take the measurement, if it's really high or really low, it's going to affect the measurement. It also is affected by the chloride content or effectively the admixtures or if the concrete is carbonated or not. A really good guiding tool, but you cannot solely rely on resistivity values to give you all the answers. Another technique we often use is acoustic method. It's called impact echo or pulse velocity. Essentially, the technique relies on sending a mechanical wave or a sound wave into the concrete and analyzing the velocity of the sound wave traveling through the concrete or analyzing the frequency of sound wave that's traveling through the concrete. Just by analyzing these two parameters, you can tell a lot about the concrete properties or if there are any issues with the concrete. In terms of the instrumentation, you send a sound wave into the concrete using a pneumatic impactor, which is shown here on the top right and the top bottom right images. You make an impact on the concrete using a steel ball bearing, and you wait for the signals to pass through these four sensors. And just by measuring the velocity and the frequency of the sound wave, you can know a lot about the concrete. Now, imagine this box to be, or blue box to be, a block of concrete and this horizontal white line to be a defect, let's say a delamination or a crack. When you make an impact or when you pass the sound wave, this is how it would reflect. The sound wave will reflect from the defect itself. So just by measuring the time, you can tell a lot as to what the defect is or how widespread the defect is. And also the sound wave reflects from the back surface. So if you don't know the thicknesses of your element, impact echo can also tell you a lot about your unknown thicknesses of your elements. And then effectively you're measuring the velocity or the frequency. Impact echo, as the name suggests echo, we are looking for the reflections. We are looking for the frequency, and it can give you the thicknesses of the unknown concrete elements. It will also give you an idea about if your concrete has micro cracking or it has potential delaminations or any potential concrete consolidation issues. It can also give you strength in the thickness direction. Whereas pulse velocity, we are measuring the velocity of sound passing through the concrete. The higher the velocity of sound through the concrete, the higher is the compressive strength of the concrete. That's the rule of thumb. When I'm talking about the strength of the concrete, I'm talking about the dynamic in situ compressive strength of the concrete. We can easily relate this into, we can easily correlate this to the compressive strength you would get from the the concrete cylinders you would test for compressive strength. For newer structures, the correlation between impact echo and the cylinder break test can be as good as 92 to 95%, whereas for older structure, those correlations drop down to, let's say, like 85 to 87%. And in most cases, we have come across the compressive strength as close as 50 psi. So these techniques are really accurate in assessing the strength. This is a really good case study where they had a car fire in a garage in New Mexico, where the beams, the columns, and the slab under, like the deck, were affected by really high temperatures because of the fire, and that resulted in compromised strengths of the concrete. And we were tasked to determine what the compressive strength of the concrete is. So we did impact echo analysis, or we did impact echo testing of the beams, columns, and the deck underside. And this is what the data looks like. Effectively, this is a heat map showing the spread or visually how the compressive strength looks like. And towards the right, you see a lot of reds and yellows. And if you look at the scale, these are the areas where the compressive strength has dropped down significantly. And then when the contractor removed the unsound concrete and we went to the base concrete, you see these two locations where the strength were relatively higher. So impact echo was successfully used on this project to determine if there was any drop in strength because of the fire incident. And if there was, how deep does the damage extend to? And if you remove the concrete, what are the subsequent strengths of the base concrete? So it can be a really powerful technique without even taking any destructive concrete cores. This is another example of a compressive strength heat map for an abutment wall for a bridge, where you see reds and yellows showing the areas of weakness, whereas the other areas are strong. And if the owner or the engineer still wants to go for concrete sampling, you still can use this as a guiding point, where you can take 60 or 70% of your concrete cores in the bad areas and maybe 20 to 30% of the samples or concrete cores in the good areas. So that way it's a guiding direction for you as to where to sample from. So impact echo can be really impressive technique in giving you more information about your structure. Those were the non-destructive tests. One of the semi-destructive tests is corrosion potential survey. This technique will give you if your rebar is actively corroding, or if it's passive or non-corroding, or if it's within uncertain area. Essentially, what you do in this technique is you make a connection to the steel. So you do your GPR scans, you locate your rebar, you make a connection to your steel, you connect it to a multimeter, and then you use something called as a reference electrode. A reference electrode is essentially a standard piece of metal, maybe a silver filament or copper filament or a copper rod. And then what you're trying to do in this technique is you're measuring the potential difference between the reference electrode and the steel within your concrete. And just by measuring the difference, you can tell if your steel is corroding or not. And the way you would read the data is given on the bottom left. This is only for a copper sulfate reference electrode and for steel and concrete. So if you're reading the potential difference of negative 350 or more negative, it means you have high likelihood of active corrosion, or meaning your steel is actively corroding. If your potentials are more positive than negative 200, it means your steel is passive and it's not corroding. Anything between negative 200 and negative 350 is uncertain areas where we cannot say for sure if it's active or passive. So corrosion potential survey can result in heat maps, something like this. This is how the corrosion potential data would look like, where this is actually a corrosion potential survey on a ramp, where you see a lot of reds and yellows, and you see these two areas that are hatched. These are greens, where the steel is passive, it's not corroding, whereas the area surrounding those two hashed areas, it's actively corroding or is in the uncertain area. And that's because these two hashed out area, that's where they had previously done their concrete repairs. In these two areas where the steel is passive, the steel is exposed to good quality concrete without any chlorides. These are chloride-free patch repairs. Whereas as soon as you move out of these patch repair areas, you have chloride contaminated concrete, which is still causing the steel corrosion. And that is easily reflected in the corrosion potential survey. Very powerful tool. It can tell you what percent of the area is actively corroding and how widespread your corrosion is throughout the structure. This is another example of corrosion potential survey being done on an entry ramp of the parking garage. And when you do the corrosion potential survey, everything looks red. Most of the areas look red. And this leads you to believe that the corrosion is very active, or all of the areas actively corroding. Well, when you are analyzing the corrosion data, you need to know what you are measuring. This corrosion data or corrosion potential data is from a concrete deck that is supported by a galvanized metal pan deck that is also connected to your rebar within your concrete. So when you are measuring the corrosion potential, you are measuring the corrosion potential of steel and the zinc. So you're measuring mixed potentials. So really, in that case, this scale is not really relevant to that. In that case, we employ something called as delta measurements, which is effectively taking a difference between two adjoining locations. Let's say if you measure at location 1, you measure negative 300, and in location 2, you measure negative 350. You just take a arithmetic difference between those two locations, and this is essentially plotted on the image on the right side. So when you're analyzing the data or when you're doing the corrosion potential surveys, you need to be aware as to what you're measuring and if it's truly steel or if it's steel plus some other alloy, because that can affect your results. Another classic example is this. This is an exit ramp for the parking garages, not really that many chlorides, and most of the area seems passive. But again, same thing. We are measuring zinc and steel, and when we took the delta measurements, we see a relatively higher percent of area that is actively corroding. So just by looking at the potentials in the adjoining locations, you can tell a lot about your structures. In some cases, you can use the absolute scale for corrosion potential measurements, where in some cases you really cannot use that logic and you need to employ delta potentials to see what's the relative susceptibility of corrosion in your concrete structure. In addition to non-destructive testing and some semi-destructive, we also take some chloride samples. In the areas which suffer from a lot of icing or a lot of snowfall or where the temperatures go really low, de-icing salts are often employed to melt the to melt the ice and make it drivable. But those de-icing salt contain a lot of chlorides. And when the chlorides get into contact with the concrete, they diffuse into the concrete to the rebar and they destroy the passive film, which results in the corrosion of steel. In some cases, your parking garage or your parking structure is really close to the sea coast. For instance, in Florida, we have a lot of parking garages that are very close to the beach, and that's where you would have chloride exposure because of the airborne chlorides. In some cases, you're dealing with parking garages that are underground, that are in contact with the nearby soils, and these soils can be really acidic, where the leachates from the soils can get into contact with the concrete and lower the pH of the concrete. And just the lowering of pH of the concrete can result in corrosion of steel. So chlorides can come from various different sources. And the problem with chlorides is once the chloride get in, they are never coming out unless you do something about it. Chloride always act as a catalyst. They never participate in the corrosion reaction. They just accelerate the corrosion reaction over and over again. And that's why it's important to know how much chlorides are present at the rebar depth and what's your rebar depth or the concrete cover depth. And those two pieces of information can be gathered from either GPR and also doing some concrete sampling. So to understand what's the chloride risk or what's the risk for corrosion induced by chlorides, you need to know how much chlorides are present at the rebar depth. And for that, we do some concrete sampling starting at the concrete surface and going all the way up to the rebar depth. We can take samples in the form of concrete core and analyze the chloride content at different depths, or we can also take samples in the form of powders, and we can analyze the chloride concentration. These this vertical green lines is essentially concrete cover depth. Remember, I said the higher the concrete cover depth, the more service life you can usually expect from your structure. Because if you have a higher concrete cover depth, this vertical green line will be shifted towards right, and you will have more time before the corrosion can start. And second is, what's the minimum amount of chlorides you require before the corrosion can initiate? It's not that as soon as the chlorides get to the rebar, they will start corrosion. It does not happen that way. You need a specific amount of chlorides for corrosion to initiate. That is what we call as corrosion initiation threshold or critical chloride concentration. There is a wide range for that based on the concrete material you're dealing with. But for conventionally reinforced structure and for service life modeling purposes, we assume that value to be 350 ppm, but there is a wide variability associated with that. So when you are doing concrete sampling, you need to know what is my chloride content at the rebar depth and if it is higher than corrosion initiation threshold. If your concentration at the rebar depth is higher than the initiation threshold, it's highly likely that your structure is suffering from corrosion induced by chlorides or chloride induced corrosion. If this last point or last data point is below this line, then it's likely that it's going to take a few more years before the corrosion might start. But this corrosion initiation threshold and the rebar cover depth is really critical pieces of information. In addition to knowing how much chlorides are present at the rebar depth, we also need to know if your concrete is acidified or not. And this is especially true when you're dealing with parking structures. In parking structures, your concrete is exposed to vehicle emissions, carbon dioxide, carbon monoxide, sometimes sulfur dioxide. And these species can diffuse into the concrete and cause acidification of the concrete or lowering of the pH. The pH of a good quality concrete can range anywhere between 12.5 to 13.5. Whereas if these species get into the concrete, they can lower the pH to about, let's say, 9. There is a quick test we can do in the field. If we are taking concrete core out of the structure, or if you're exposing a fresh concrete surface, we spray it with a pH indicator spray or a phenolphthalein spray, and that can tell you if your concrete is acidified or not. If your concrete is acidified, the color will be colorless. There will be no color. But if your concrete has a high pH, the color will be pink or purple. It will turn its color into pink or purple. This is a really good example where concrete is acidified from the front and also from the back. The front is acidified because of the carbonation, whereas the back is acidified because of the presence of acidic soil on the backside. Whereas the center of the concrete is still maintaining its high pH and still protecting the steel. So if your rebar falls within the pink or the purple zone, we are good. The concrete is still protecting the steel against corrosion, and it will maintain its passive oxide. But if your rebar falls within that colorless zone or a low pH zone, that's where the corrosion would happen because of lowering of the pH. That's where your passive oxide film will be destroyed, and that's where the corrosion will start to begin. This is essentially what you see in the carbonation. In some severe cases where you have spalling, and we often have to rely on section loss measurements because structural engineers often need that piece of information as to what's my load-bearing ability of the steel. In those cases, in those severe cases, if we have a rebar that's accessible to us, we can take section loss measurements to see how much loss of diameter has happened or how much section loss has happened over the time. If your concrete is still sound, but you suspect that the corrosion is happening, you can make an opening and expose the steel and measure the diameter or the remaining diameter of the concrete, of the steel. So far, we have been attributing most of the corrosion, concrete issues or deterioration issues to corrosion of steel. Well, that's not necessarily always the case. You can have concrete cracking or spalling because of other issues beyond corrosion. In some cases where your concrete or your area is experiencing freezing and thawing cycles, the water within your concrete can freeze up, it can expand, and it can crack the concrete. And again, it can be thawed during your warmer temperatures, but during freezing cycles, it again expands and cracks the concrete. This is essentially what you see on the bridge on the left side, where concrete is experiencing freezing and thawing cycles. Once you lose that concrete cover, your rebar is exposed or your rebar has a very minimal concrete cover, and that can result in a significant reduction in service life because now your chlorides can easily get in, your all the deleterious species, your moisture can get in quickly and start corrosion of steel. So freeze thaw can be one example that's where corrosion can be cracked or spalled, not because of corrosion, but because of something else. Second issue we often run into is alkali-silica reaction, where you have siliceous aggregates in your concrete mix, and you have a high alkali content in your concrete or in your cement. And when you have a lot of moisture, you form something, a reactive gel, or a byproduct of the ASR is a gel, which is very expansive in nature, and that results in cracking of the concrete. So that's alkali-silica reaction. In parking structures which are exposed, or like underground parking structure which are exposed to acidic soils, you can have something called as a sulfate attack, where the sulfates in the soil can attack the cement paste and eat away the cement paste, thereby making sure that the concrete is cracked or the cover depths are reduced. In order to assess all of these issues, there is a really elegant technique called Petrographic Examination. This technique will give you a lot of information about your concrete. If your concrete has reactive alkalis, if your concrete has micro or macro cracking, if your concrete has any voids, what's the void structure, how widespread the freeze thaw damage is, how widespread the ASR is, what's the level of damage, what potentially is the water to cement ratio. You can get a lot of information from petrographic examination. And for this examination, typically you need a 4-inch diameter core, and you can just do this microscopic examination, and it will give you a lot of useful information for your structures. Again, petrographic examination, these are a couple of things you might be able to see using this examination. Very valuable technique, but that needs a 4-inch minimum 4-inch diameter concrete core and a relatively long concrete sample. Now, we have been talking about steel that was exposed or that is exposed to concrete. In some cases, we are dealing with steel or alloys that are exposed to air. Air is a really bad electrolyte when it comes to testing, and there's only so much we can do about it. One of the few techniques we can use is ultrasonic thickness measurements, where you can just measure what's the remaining section of those air exposed steel or alloys if you have been experiencing any section loss, or if there are any internal defects that are present in your steel members. This is a really good example where we were dealing with a concrete deck supported by a galvanized metal pan deck. And in some cases, you were seeing through holes in the metal pan deck. But in other cases, you were seeing partial section loss. And that's where you prep the sample and you measure, you take the ultrasonic thickness measurements and you see what is the section loss you are seeing overall that is spread out through the garage. So ultrasonic thickness measurements can be really useful tools when you have atmospheric exposed steel members or metal members. So in conclusion, corrosion is inevitable. We can just slow it down or we can delay it. Evaluation or using different techniques in conjunction will give you a really comprehensive picture about your structure. You cannot simply rely on just the hammer sounding or just the visual inspections. You need to use multiple techniques at the same time to get a more confidence in your data and the more information about your structure. And finally, understanding the exposure environment and the required service life is the key to designing proper long-lasting repairs and designing proper corrosion mitigation strategies. And essentially, that's what I had for you today. So let me know if you have any questions and I'll be more than happy to answer them.
Thanks, Pratik. Really nice job there. And yeah, I'm glad we have a little bit of time for questions because quite a few came in. So I'll just get right to them now. There was a couple right at the top that came in. So they're all going to have a little bit of the same theme for these first couple, where it had a lot to do with corrosion inhibitors and some things placed in the mix. So when you're dealing with corrosion inhibitors placed in the concrete mix, how does that affect that corrosion cell or that ACME acronym that you showed a little bit earlier?
Right. So anodes and cathodes will always be there. Just that when you add a corrosion inhibitor to the concrete mix, those corrosion inhibitors can actively attack the anodic sites or the cathodic sites on your corrosion cell, and for time being passivate them. They have their effectiveness or they have their service life, after which the corrosion cell will again kick back. It does not mean that if you have corrosion inhibitors, you can let the chlorides go in. If your chlorides are constantly coming in, the corrosion inhibitors will be protective or will protect your steel only for a certain extent. After that, they will lose their effectiveness. And that's where you will again see anode and cathode formation. Anodes and cathode will always form on the steel, just that it depends what kind of corrosion inhibitors you're using. That will define if you're suppressing the anodic reaction or the cathodic reaction. Because you always have a metal, you always have electrolyte, and anode and cathode are being suppressed for time being. And that's what essentially corrosion inhibitors do. They suppress the reactions.
Okay. And I think this kind of goes along with that, and it may be very similar, but just want to make sure they're being addressed is, the common admixtures used in concrete design to create that passive oxide layer, or which additives used to help prevent corrosion.
Just by having highly alkaline concrete mix should give you a really good passive film formation. You don't really need admixtures. But if you want admixtures, you can always use corrosion inhibiting admixtures. It can be anodic corrosion inhibitors, cathodic corrosion inhibitor, or mixed mode corrosion inhibitors. There are a lot of compounds in the markets you can use. But a key rule of thumb is maintain your highly alkaline environment in your concrete and follow your water. If you can avoid moisture ingress into the concrete, you will take care of your structure for a really long time. Corrosion inhibitors can help you. It it does not do much for your structure if you're adding it from the get-go because your concrete is providing that passivity. But if that passivity was to go away, then these admixtures would kick in and protect your structures.
No, very good. And I think you touched on this a little bit, Pratik, but I think it's worth reviewing is how is concrete's resistivity related to the resistance to corrosion?
Concrete resistivity is essentially resistance of concrete toward against the flow of current, the corrosion current. You remember ACME, you're having electronic flow and you're having ionic flow as well, right? So your ions are flowing through the concrete mix. If your concrete is really resistive, you suppress that ionic flow. You're suppressing that E part of the ACME. You are making it very difficult for the ions to flow through the concrete. So you're trying to suppress the electrolytic part of the cell. And also, if you have really dense or if you have really resistive concrete, you will suppress the ingress of chlorides and carbon dioxide into your structure. So if your concrete is extremely dense and it does not have much core structure, for instance, UHPC systems, where it has really resistive concrete mix, it suppresses or it discourages the chlorides from diffusing into the concrete. So there is a two-way to look about it. One is suppressing the diffusion of species, and second is suppressing the electrolytic flow of the current.
No, very good. I think that very good explanation.
Yeah.
And this is something going back to GPR, and this person asks about the test method. Test method can supposedly detect rebar corrosion activity before concrete damage occurs. Speaking of GPR, is there anything GPR does to detect the corrosion activity of that reinforcing steel when you're looking at it?
No, you cannot. You can only tell if GPR is present and if the steel rebar is present at what spacing and stuff, and it can tell you if something is wrong with your concrete, but it cannot give you any information about if your corrosion is present or not, or if to what extent or what is the rate of corrosion. GPR cannot tell you that. Either you can do a corrosion rate measurement, which is the instantaneous measurement of the rate of corrosion, or you can use corrosion potential service to detect if your corrosion is actively happening or if it's in uncertain zone or if it's in passive zone. But GPR cannot tell you any information about the corrosion of steel per se.
Okay. Very good. And then this is another one pertaining to concrete, and we all know, when you're doing a repair or you're about to pour, that if it's not epoxy coated or galvanized or stainless, that you have the potential of rust before the pour happens. So
Right.
if you have a high alkaline or a high pH concrete, will it still form a passive coating or that passivity around the reinforcing steel if there's a little bit of rust that starts prior to the concrete placement?
Absolutely, it does. So in most cases, or rather in all construction practices, we see flash rust forming on the rebar. Doesn't matter how good of a surface prep you do, even if you sandblast the steel before you pour the concrete, you will have flash rust forming, especially in the areas where you have high humidity. But in that case, when you have a highly alkaline concrete mix, that high pH of the concrete helps you passivate that already corroded steel. It does not do anything for the existing rust. One thing to note here is we cannot reverse corrosion. We are essentially slowing it down or mitigating it. So the already existing section loss, you cannot do anything about it. You can just passivate the steel that has already corroded. You can just passivate it and you maintain that passivation for foreseeable future, as long as you're able to maintain that pH for the remaining service life.
Nope. No, I think that very helpful. And Here's another one in regards to the impact echo ultrasonic testing that you were talking about. So someone wrote in, okay, if you have a concrete member of an unknown thickness that also contains an unknown number, type, size of imperfections or cracks, how are you able to parse those results together? What kind of processing power does it take, or give them a little insight behind how you guys bring together all that data?
Right. So the depth of analysis is defined by the spacing of the sensors. The more widely spaced the sensors are, the deeper you can look, because you can now wait for reflections for a really long time before they come back, because of the spacing. So typically for our standard setup, we can analyze the section thicknesses up to 4 feet thick. But if you want to go into geophysical range, then we will have to use different sensors and more wider spacing. Uh, for regarding the depths, it's better to have some benchmarking or good quality concrete to cross-reference our data. It's always a good practice to take some test shots on good quality concrete and then do a survey on the entire structure. So that way we have some benchmarking. But we need to have a baseline before we can analyze the defects and the existing thickness in the absence of any drawings.
And, sticking with impact echo, somebody else asked about the calibration of it, and does it have to be calibrated with sampling or different construction data? They actually referenced the rebound hammer, or can you test with only impact echo and still get the results that you were hoping to find?
We can just use impact echo. In terms of calibration, we can do an on-site or on-field calibration where you have really good sections of concrete, where you can take some test shots and you can calibrate, okay, this is where the reflections are really strong, or we are getting really good peaks. And then you can start analyzing the entire structure. That's essentially what our baseline is. And then we have extensive library of different materials and what the sound velocity looks like in those materials. So we can always cross-reference with that as well. But having test shots or benchmarking shots before you start your actual test really helps.
Yeah, well, that's helpful. And another one in terms of kind of life cycle of the structure, and this is I'm interested to get your opinion on this one, is when localized concrete breakouts note partial surface rust, does that give you any indication of how far along the corrosion process is at this point, or what factors do you take in to say, okay, this is where you might be in the life cycle of your structure?
That's a good question. So there are multiple ways to look at this. If you're purely relying on visual inspections, obviously the answer is no. We cannot say for sure that at what stage you are at. But if you're using corrosion rate, if you're using corrosion potentials, and if you want to do some section loss measurements on the steel, I can tell you for sure, like, this is how much the corrosion has progressed so far, and this is the remaining section loss. So before you lose load bearing ability, you need to use half cells, corrosion rate testing, and section loss measurements to tell you, okay, this is so far what we have seen, and this is what to expect for the remaining service life. This also depends on knowing how much chlorides are present at the rebar depth. So concrete sampling also helps immensely. If you're seeing a widespread delamination issue or concrete spalling issue, then testing the concrete for its strength also helps. So just taking a few cores or doing impact echo on the concrete can immensely help you determine, okay, this is an advanced form of deterioration. This is in initial stages, and you should expect, let's say, 3 to 5 years of service life before you start seeing extensive delaminations of spalls in your structure. So just using one technique, I cannot give you the answers. I need to know multiple pieces of data before I can conclusively say, okay, this is where your structure lies at this point, and you have these many years before you see substantial amount of spalls and delaminations.
Nice. Okay. And moving along, here's another interesting one, and I think you touched on it a little bit within the presentation, but again, worth reviewing, is do these NDT methods help guess the correct diameter of corroded reinforcement? That is, does it have an increased diameter, or is it rust jacketed around there? Does that allow you to give a glimpse into what that might be?
GPR cannot tell you a rebar size. there's a tool called patchometer that can give you a high probability of a suspected rebar size. The confidence is not 100%. You need to either open up or make a small opening, let's say a 6-inch by 6-inch opening to actually physically measure the rebar, but GPR cannot tell you a rebar size. You can guesstimate, but that's essentially a guess.
So, okay, and here's one in regards to pre-stressing strand is, are there any methods available, and if so, what are available to detect or monitor corrosion in debonded pre-stressing strands where the strands are intentionally unbonded near the ends?
If they are unbonded or if they are not connected to any surrounding steel, then it gets tricky. Yeah, I cannot think of a technique which might successfully give you if your strand is actively corroding or not, and GPR might be able to locate that, but that's just about it. In terms of actually knowing if the corrosion is happening or not, or like corrosion potential surveys, for instance, you really cannot make a guess, or you really cannot tell much about it where it's completely unbonded or isolated from your adjoining strands. And I'm specifically talking about the strands that are buried deep within the structure. I'm not talking about the surface strands. Surface strands are easy to investigate. You can easily make a connection to those strands and take a measurement. But if you're talking about the strands that are second layer or third layer into the reinforcement, you really cannot investigate that thoroughly without the subsequent or the shallower layers influencing your data.
Excellent. And we have time for maybe a couple more here. So someone asked, and you mentioned this in your presentation, Pratik, that once chlorides are in there, there's really, you have to deal with them in some way, shape, or form. And somebody did have a follow-up question to that is, what are the ways high chlorides in concrete, is handled? Can they only be reduced by installing new concrete and chipping out that old existing concrete?
There is a technique called electrochemical chloride extraction, where you make a connection to your steel and you pass current through the steel, or you pass negative charge through your steel, and that negative charge pushes the concrete away from the rebar towards the surface, and you have a positively charged anode on the concrete surface. So positively charged anode surface on the concrete will attract the chlorides towards itself, and the negative charge on the rebar will push the chlorides away. So there is a way to extract the chlorides from the concrete that's called electrochemical chloride extraction. It's a relatively slow process, and there are some constructability criteria where this technique is applicable. You cannot really apply this solution to all the structures you're dealing with, because this technique can take somewhere between like 4 to 6 weeks for successful chloride extraction. That being said, in some cases, if you're dealing with acidified concrete, there is an add-on to this electrochemical extraction, chloride extraction, or ECE. We call it electrochemical realkalization, where you restore the pH of concrete. If you are dealing with carbonated concrete, you push alkalis into the concrete to increase the pH from, let's say, 9 to about like 12 or 13. Again, a relatively longer process. It has to meet some criteria before it can be used on any element, but you can take the chlorides out. But unless you apply electric potential, there are only a few ways you can take the chlorides out. Either take the concrete out or replace the contaminated concrete and replenish it with a good quality concrete, or use electrochemical chloride extraction. And this will be covered in subsequent presentations in the series. I believe third or fourth presentation in the series is going to talk about this technique to extract the chlorides.
Excellent. Yeah, no, thank you for that explanation. And it kind of goes along into those terms of going back to your corrosion potential survey. And if you have widespread issues,
right,
are you able to survey at just discrete points, or how would you plot a corrosion potential mapping throughout a large area?
So there was an image I just showed you. Just let me go to that slide and I can explain better. So the gentleman here is doing a survey at a discrete location. So you take corrosion potential measurements every 2 feet grid. If the area is really large, you can have a 3 feet by 3 feet grid, and you take a measurement every 3 feet in X and Y direction. Whereas you also have access to this wheel where you just walk with this wheel and it constantly measures the potential at a set interval. You can define that interval. It can be every 1 feet, it can be half a feet, it can be 3 feet. But effectively, we are talking about discrete corrosion potential measurements and stitching them to form a corrosion potential heat map you see here. But these are discrete measurements, yes.
Okay. And sticking with that, you may want to stay on this slide or with these couple slides when someone also asked the question of how do you fine tune your half cell potential maps when readings may come from different types of metals that are being picked up?
Right. So for instance, here is an example where we were essentially finding that the reinforcing or like the welded wire mesh in the concrete was electrically continuous with the galvanized metal pan deck. And when you're measuring the potential, you're not just measuring the potential of steel, you're measuring the potential of the zinc as well. And that's where you really cannot use this scale. You need to use delta measurements. You just take a difference between two adjoining locations, because a difference between two adjoining location is the driving, like a driving voltage or driving factor that drives the corrosion. The higher the difference between two adjoining locations, the more is the susceptibility towards corrosion. For instance, if the potential difference between two adjoining locations is 100 millivolts, it's almost certain that the corrosion will happen in near future because you're forming small macro cells in these areas. And that's why you really cannot use this absolute potentials, because this is only applicable for copper sulfate reference electrode and steel in concrete. This ASTM 876, it does not, this scale especially does not really apply to zinc or anything. It has to be applied to just steel. And that's where the delta potential measurements come into picture. So it's all context, like what are you dealing with? What are the environments? What are the different metal systems you're dealing with? And you need to analyze the data appropriately.
No, excellent. And then there's one more follow-up for the potential survey, and it's how many rebar locations need to be exposed to be connected, even if they only have one mat of rebar. Somebody made the example of, say you were doing a bridge deck.
Yeah.
And how many openings would you need, and how would you go about that?
As long as the rebar mat is electrically continuous with each other, meaning they are physically touching each other, like steel to steel contact, we can just have one connection made for the entire parking garage deck or a bridge deck, and you can do the entire survey with just one connection. That being said, if you're dealing with, let's say, epoxy coated steel, this technique does not really work there because you're not having steel to steel contact. You're having coating to coating contact, or in some cases where the coating is completely gone, you're having a coating to steel contact. So the prerequisite for this kind of survey is that your structure is electrically continuous or your rebar is electrically continuous, either by means of ties or stirrups. If your rebar is electrically touching each other, you can easily do this survey. So if assuming that your rebar is electrically continuous, just one connection per element or one per entire concrete deck should easily work for you. And this hole is like 5/8 inch thick or like diameter or half-inch diameter in some cases.
Excellent. And last one on corrosion potential survey while we're at it. Someone said, okay, say I had about a 10,000 square foot parking garage, and maybe it has to be fully done or partially done. How much time does something like that take? And are there any points to keep in mind before doing the survey?
If we are able to establish electrical continuity, like if everything is continuous, I can easily do 10,000 square feet of survey in like one day, especially with this wheel electrode. You're simply walking across your parking deck. One connection suffices. You're walking every 2 feet increment, and this automates the data collection so it can be very quick. So 10,000 square feet easily one day. In some cases, even faster. If you have two teams going at the same time, you can easily finish it in half a day. But it all depends what the temperature is, if you're electrically continuous or not, if there is any waterproofing coating, because this technique does not really work if you have any traffic membrane or asphalt overlays on it. It has to be bare concrete surface. In such cases, we do the survey from the underside, and doing the survey from the underside can be time consuming.
Excellent. And then, I think we're going to wrap up and do maybe one more. I know we're running a little bit late, but let's see. How about we'll wrap up with this one. For a parking structure application, can reinforcing an existing concrete beam with exposed structural steel connected from the underside and in direct contact with the concrete lead to corrosion of the steel? Will using galvanized steel mitigate that corrosion?
Could you repeat that, Eric?
Yeah.
Could you repeat that question again?
Say we're in a parking structure application, right?
Yeah.
Can reinforcing an existing concrete beam with exposed structural steel connected from the underside and in direct contact with the concrete lead to corrosion of the steel? So it almost sounds like you're doweling in a new or adding an existing steel into your repair. And then will that lead to corrosion of the steel? And also, what if they substituted in a galvanized steel in that repair?
It may, depending on how contaminated your concrete is. If you are putting new steel in chloride contaminated concrete, then obviously it is going to corrode. Even if it's galvanized, that galvanizing layer will be easily consumed, and that zinc will be easily consumed, and it will lead to corrosion. It's just a matter of time. It's just a matter of when rather than if. It will corrode if you're dealing with chloride contaminated concrete or contaminated concrete. But if you're still dealing with high quality or good quality concrete where the high alkaline nature is still maintained, then the chance of corrosion is very low. Whereas if you're talking about steel outside the concrete exposed to air, you have different issues. If you have coating failures, you can have corrosion. If you have any dissimilar metal contact in air, you still can have galvanic corrosion. So it all depends, but we can always discuss the project specific details, and I can have more inputs if I know exactly what's happening at the project.
Thanks, Pratik. And again, a really nice job. There's a lot of comments in here about great presentation. So nice, really nice work. And thank you for doing it.
Really good questions, I must say. Really good questions.
Yes. And there's a lot more I couldn't get to. So with that being said, Pratik will be reviewing these, and for the questions that he didn't get to, he will be reaching out over email to respond directly and make sure that we're following up with everybody. So again, thank you to everyone who took time out of their day to join us today. I hope you found it informative. Pratik, really nice work and really nice job presenting. We appreciate you taking the time. And yeah, look forward to seeing everyone on December 3rd at our next webinar. And yeah, let's get out there and save some structures. Thank you, everybody.
Thank you, Eric. Thank you, everyone.